Thank you all for coming today. I am very excited about our speaker, who is Michael Stein, who has been spending this semester with us as a distinguished visiting fellow in EOAS and a visiting distinguished professor in the Department of Statistics. He's also been teaching a Earth System Statistics course, which we think we have about a dozen EOAS students and a few stats students participating in, which has been going great so far, I think. Michael comes to us from the University of Chicago, where he has been for about 30-some years. Prior to that, he did his degrees at MIT and at Stanford. And he's really pioneered a lot of the work on spatial temporal statistics. I know when I'm sitting in class and he's been giving some lectures on spatial temporal statistics and stuff, I use it a fair bit. I'm sort of getting it from one of the people who did some of the key early work on developing these methods. And he's going to talk to us today about a couple of the statistical problems in environmental science. Michael.
All right, well, so thank you for coming. So I'm a statistician, so if I say something silly about climate or tides, don't hesitate to let me know. So the work I'll be talking about, at least the first part, the co-workers are Matt Haugen, who's a postdoc who's now in private industry, Ryan Shriver, who's at University of Illinois, and Elizabeth Moyer at Chicago. Okay. So I want to talk about some specific things, but I also want to talk about some general principles. So how should we do future climate simulation? Well, so what information do we have about it? Of course, we have our theory, which is important, but I'm trying to simplify things by just looking at the two things that people most think about that we have for telling us about the climate. We have actual observations. Okay, and we have model output. And we have the present and the future. And so, the observations are hopefully the most reliable piece of information we have, although observations have their own problem. We have them for the present, but we don't have them for the future. And of course, the model output, the advantage of that is we get it both for the present or at least some hypothesized future. So the problem is we have no direct information on the cell of this two-way table that we're most interested in. All right, so how should we go about doing this? Well, I don't think anybody proposes directly using the model output as a good way of simulating future climate, because we know there's all kinds of biases in the model output and we want to correct for them in some way. Okay, so if you have a two-way table where one of the cells is completely missing, you have no direct observations on the interactions. Okay, so the simplest thing to do is to say, well, there won't be any interactions and just assume some kind of additivity. So if all you were trying to predict was a single number, then you could just do the arithmetic and say, okay, if this table were exactly additive, what should I put in there? And then you could be done. But of course, climate's not a single number. Climate is this very complex and rich multivariate space-time process. And we should hope that our future simulations should capture those dependencies in some kind of fairly realistic way. Okay, so I'm an advocate of a certain point of view on this, and I call this the do no harm principle of climate simulation. So unless you have some meaningful reason for thinking that the future will be different from the present in some specific characteristic, in some specific way, then I'd rather use the model observations the actual observations to say what that feature is going to be like than to try to get it from the model. So in particular, the simplest kind of way we can imagine that our models are wrong is that they just have the means wrong. Otherwise, our models are perfect. They capture all the multivariate dependencies. They capture all the space-time complexity perfectly. They just have the mean wrong, and we just have to correct for that. Okay, if that were the case, then there's basically kind of two standard methods for trying to correct things. There's bias, what's called bias correction, and that tries to say, okay, let's use the future model output, but correct its biases by looking at the differences between the present model output and the present observations. Okay, so it takes the future model output and corrects them with the present bias. That does not satisfy this principle, right? Because that uses the model output to say what all those dependencies are like, okay? And I find it highly implausible to imagine that models get those kind of complex dependencies accurately. Okay, so the other kind of main method that you could try to use is kind of reverse the roles of things and to mean shift the observations. Okay, so let's take the observations and shift them by this difference in means. Okay, this, at least in principle, satisfies this do no harm principle, right? Because it reproduces all the space-time dependencies in the observations, it just corrects their means. Okay, but no one really thinks that it's only in the means where climate is going to change, and so we need something more complex than that. All right, so I first gotten, well, I shouldn't say first, but in my recent incarnation of my research, I first got involved in this problem several years ago where we were thinking about, well, what about the variability and temporal dependence? So it's just it's a space-time process, climate. That seemed too much to look at. So we tried looking at just daily temperatures and just at a single site at a time. So what could be wrong in terms of the variability structure is both the variances of single observations, but also the correlations in time. All right. So how could we, so we wrote a couple papers where we looked at this issue, and so the idea is we used model output to learn about how temporal dependence would change. And the way we looked at temporal dependence was by looking at the spectra of the processes in time. And we could see in the model output that the model really did think that the spectra would change. It depended where you were. In some places, the whole spectrum would kind of move down. In some places, the low frequencies would go down and the high frequencies might go up a little bit. And we tried to learn that from the model output and then applied that to the observational record to kind of adjust the model observations to look more like the future. So this was an example of so again, we were only using the model output to learn about how the climate changes. We didn't need the model to be accurate in terms of its actual representation of the present climate. Okay, and so this first paper just looked at a simple setting where there were two climates, two stationary states, some mythical present state and some mythical future state, and we just would adjust between them. But we don't live in stationary climates. We live in a transient climate, and so we wrote a second paper where we tried to say how to do this in the transient setting. Okay, but this kind of approach, all it did, in taking kind of discrete Fourier transforms of observations, and then adjusting things and adjusting back, transforming back, everything was linear. So this can't have anything, this can't do anything about shapes of distributions. So this would be great if daily temperatures were a Gaussian process and all you had to do was change the spectra. Okay, all right, but temperatures, if you look at them at all carefully, are clearly not Gaussian. So as one example, as we're going to see, although it shouldn't surprise anybody here, is that in the wintertime, the lower tails of temperature tend to be fatter than the upper tails. So you can get in a place like this, or Chicago, where I've been, you can get these really bitterly cold days in the wintertime. And so temperature distributions in the wintertime in a lot of climates, places at this latitude tend to have this skewed left distribution. Okay, so that's clearly a non-Gaussian feature, and it's something that might change in the future. Something that might feature and something that might change in the future. Okay, so as computers get faster, the tendency is to try to say, oh, let's make our models higher resolution, let's add more processes. But I think there's been a recognition in recent years that another advantage of faster computers is to run our not quite so high resolution models more often. That we can learn something useful, at least about climate model world, by running multiple realizations of the same climate model, and in particular, exactly the same climate model, just with different initial conditions. So there's these initial condition ensembles that are out there, and SFK is Shriver and two of his co-authors. They did a 50 initial condition, 50 run initial condition ensemble of CESM, T31, quite low resolution. And they're all under this RCP 8.5 scenario. And I don't have to explain what that is to this audience. All right, and so the idea we had for thinking about dealing with the non-Gaussianity was to do what's called a quantile regression. And I'll just explain it a little bit. But in part, the reason that we can kind of do this successfully is because we have so much data. That is because we have these 50 runs, each of 250 years, we can get away with using quite flexible methods and still get very good estimates of things. All right, so basically it's a form of regression, but instead of mean regression, it tries to estimate quantiles. So you can pick the quantile you're estimating, and you get a different regression for every quantile. All right, so what are the functions that we're using here? So we want to think of the quantiles of temperature as a function of the day of the year and T, the kind of the long-term time. So in some sense, D is a function of T, but I really want to think of T as the long-term effect and D as the seasonal effect. And so we have to pick some basis functions, these xj's, and then we estimate these coefficients which depend on the quantile alpha. And this allows us to map out the distribution of temperatures as a function of the day of the year and the year. And we can do this for 1850 to 2100 because that's the runs that we have. All right, so I have to pick these basis functions, and we just kind of pick some what we thought reasonable basis sets for doing this. So seasonality is obviously an important effect, and so we include a lot of seasonal terms. We include a smaller number of terms for long-term changes, because the long-term changes, while they're not linear, they don't have show that much complexity to it. And then importantly, we included interactions, right? So if the seasonal cycle is going to change over time, and I think you would all imagine that it will to some extent, you can't just have a seasonal effect and a long-term change. You need an interaction between the two. So we have interaction terms as well. And then as a method of looking at the results, we wanted to look at, instead of just things like moments like means and standard deviations or even skewness, which is a kind of measure of asymmetry, we wanted to look at the left and the right tail separately. So the interquartile range is just a measure of kind of bulk variability, so it's a kind of a robust substitute for the standard deviation. But then we wanted to look at how spread out the lower and upper tails were. So this is a difference between two lower quantiles. This tells us how spread out the lowest temperatures are, and this one tells us how spread out the upper temperatures are. I'm going to show you results for pixels that kind of correspond to those three cities. And then I'm going to show you what these estimated quantiles look like over time at years 1850, 1890, 1930, up through 2090, where blue is the earliest years and red is the latest years. And we're going to give you uncertainties too, and this is one of the places where the ensemble really makes your life easy, right? Estimating uncertainties when everything's dependent on everything else can be tricky because those dependencies affect the uncertainties of your estimates. But if we're willing to assume that the different members of our ensemble are independent of each other because of the sensitivity of initial conditions of climate models, then we can get away with just assuming those are independent and don't have to model any of the dependence within any of the ensemble members, and we can get valid uncertainties. So the uncertainties I'm going to show you are based on that. Okay, so it's almost hard to see, but the solid lines are the point estimates of the quantiles, and the dashed lines are the uncertainties. And what you can see is that the dashed lines are very close to the solid lines. So because we have so much data here, these uncertainties are quite small. All right, so let's look at what these show. So this middle one's the interquartile range. Here's the lower tail and the upper tail. This and this are the same scale. This and this are the same scale. So the two tails for each city are the same scale. And so what can you see? That at all three sites, the lower tail is fatter in the wintertime, and in the wintertime, it's much fatter than the upper tail. Whereas in the summertime, maybe the distribution looks reasonably symmetric. All right, but in the wintertime, it's definitely skewed left. Okay, so how do things change? Well, the upper tail doesn't seem to change at all. It doesn't mean that the high temperatures aren't changing, just saying that the spread in high temperatures doesn't seem to be changing according to this model. Now for the IQR, we have at the southernmost site, not much is happening. but at these two sites, the two more northern sites, there's definitely decreasing variability as you move into the future. Okay, so variability goes down as you move into the future. And what about in the wintertime? The wintertime up in Calgary, there's not much change over time, but especially at the southernmost site, the variability in the wintertime is the spread in the lower tail in the wintertime is going down. So this compression of lowest temperatures at the southernmost site. I think one interesting thing about this picture is that none of the sites, at none of the seasons, at none of the quantiles, is there any clear sign of variability increasing. Okay, so if you, probably not a surprise to a lot of people here, but if you ask someone in the general public who tries to stay informed about climate issues, you ask them, is variability going to go up in the future? They will say yes, and if they've read loads of articles that are about that. Okay? I think at least for temperature, maybe for precipitation, there's some real evidence, and for temperature, my understanding is there's very little evidence that variability will increase. So you hear about more extremes. Well, that's just because, of course, if things get hotter, you're going to get more hot extremes. That doesn't mean things are more variable, right? In fact, the temperature distribution, I think there's good reason to believe that it'll compress somewhat as climate change effects accumulate, right? That we're going to warm the coldest temperatures much more than we're going to warm the warmest temperatures, right? That's kind of what you expect when you put a thicker blanket on the Earth. So, all right. All right, so I think I probably said most of what's here. Okay, so you know, obviously people have tried to look at these kinds of effects, but most, and I wouldn't say all, but most of the papers we could find where people try to look at these kinds of things, they say, well, how do we deal with seasonality? We'll just look at the data separately for every season. And how do we deal with changes over time? Well, we'll have a present block and we'll have a future block. That involves making these kind of arbitrary barriers and picking boundaries. And you know, a 3-month season, especially if it's spring or fall, there's a big difference between the beginning of March and the beginning of May in Chicago, and I think I'll find out that it's true here too. You know, but even if your season is just a month, the beginning of April and the end of April is noticeably different. And so I'm much happier with trying to fit these smooth continuous basis functions. I think they provide a much more realistic representation of what kinds of things are going on. I mean, I think there's all kinds of subtleties here that you would just miss if you broke things into seasons. So I prefer this kind of approach. That being said, I think one could do better in some places here. I'm not completely convinced some of these smaller wiggles are real. They might be artifacts of the basis functions that we're choosing. All right, so this is the first paper we wrote on this topic, and then we've recently written a second paper where we wanted to be able to use this approach to do future climate simulations. This first stuff was just kind of descriptive of the model. It's not telling you how to simulate a future climate. So how would I use this? How would I combine this with observational data to say what the future climate would look like? Okay, so I'm going to need to define some notation. There's going to be some equations. I'll try to talk you through them. Okay, so I'm going to use X for observational record as a function of the day of the year and the long-term time. Y is going to be the model temperature, but it's got a subscript J because I've got many realizations of the model output. Let's write TP, so P is kind of for present. That's a year for which I would have both model output and observations, and TF would be some future year for which I have only model output and not observation. Okay, and for not necessarily good reasons, instead of defining the quantile function, I'm going to define the cumulative distribution function, which is just the inverse of the quantile function. And I'm going to use F for the cumulative distribution function of the observations, and G for the cumulative distribution functions for the model output. And now this does not depend on J, right? We're assuming that the statistical law of the climate doesn't depend on the initial conditions. It's not. So G does not depend on J. So bias correction would probably correspond to something like this. You would take model output in some realization for some future year. You would transform, is that the right way? All right, well, let's hope that's, yeah. Right. Well, this is what we're, okay, I mean, I think there's more than one way of doing it, but this is one possibility. you transform this to a uniform scale, and then you undo. This feels backwards to me. I would prefer this to be P, P, F. I think all the P's and F's should be switched around here. But no, that's right. Okay, so this is the model output for the future, and then we're going to bias adjust it. But then there should be some present. Okay. Okay, I guess this makes sense. I'm not sure this is the only possibility. Okay, so this is the future model observation output, and we're going to adjust it by looking at how. So the point is, how are these two different? This uses the model output's present CDF, and this uses the observation CDF, and so that is a way of doing bias correction. Okay, so from the point of view of having it, in addition to not satisfying the do no harm principle, this is another problem in the present setting. So look, we have lots of observations or lots of model output to tell us about this G function, but we only have our limited observational record, which, if we're using reanalysis, which would often be the case, and only about 40 years of observations to estimate this function. So we have these G's, which we can estimate really well, and then this F, which we can't really estimate very well, and that kind of really undermines our statistical uncertainty about things. On the other hand, it has the advantage of that because it only uses the observations to estimate this. It doesn't need, notice there's no X's on this side. I can do as many future simulations of climate as I have simulations. So if I have a big ensemble, there's an easy way to simulate lots of futures. Okay, so here's a very simple version of delta change, not what we're going to end up doing. So now I really am using a present temperature. This is an observation. I transform it to uniform using the model, what the model output thinks the temperature distribution is, and then I transform it to the future using that. So this has the advantage of that the only CDFs I have to estimate are of model output. I never have to estimate F. I just need the data, I don't need F. And that helps because F is hard to estimate from the limited data. On the other hand, I have no obvious way of doing multiple simulations because I only have one of these X's. So that's the downside there. Now, this does satisfy do no harm in the sense that whatever are the spatial temporal dependencies in the observational record, those will largely be reproduced in my simulation. All right. But we thought this really wasn't good enough because the biases at some places and in some seasons can be so substantial. I don't really, suppose this temperature is a temperature that never occurs in the model output. I feel a little bit uncomfortable transforming that, using a model output CDF. So we decided to first normalize things. I'm not sure how much I want to go through these details, but it doesn't matter that much. All I'm really trying to do is put the observations on the same general scale as the model output so that I don't get a temperature here that looks really different from anything I've ever observed. So we first did a normalization, and then the normalized observations have a tilde on them. All right, so then the delta change turns into this much longer equation, but it's really it's just the same idea over and over again. There's a normalized observation, there's a normalized CDF to hopefully transform this, a back transform using the future, and then I undo the linear normalization. Okay, so this tries to fix the scale, and this part tries to fix the location. Okay, so there's basically, for this to really be the right thing to do, you need three things to be true. You need these two things to be equal to each other, this kind of forward and backward transformation of the CDFs. This is saying that the shape of the distribution in the observations, not the shape itself, the change in the shape in the observations is going to be the same as the change in the shape in the model output. Now, if we're not willing to make some assumption like that, we can't proceed, right? It's that fourth cell we don't have. So we're hoping that'll be close to being true. The second one says that the location, the mean, the median, whatever you want to use, for the model output is similar to what the change in location for the actual observation is going to be, and this is the same thing for the scale. So in all three cases, we're only using model output to look at how the world's going to change, how it's going to change in shape, how it's going to change in scale, how it's going to change in location, as a function of D and T. All right. I think I might skip some. There's a couple of little details here. I'll skip the bottom half. The top half is important though. So how should we, okay, so where do I get all those Fs? I mean, the rescaling isn't that big a deal. The hard thing is where do I get those F tildes and G tildes from? Or the G tildes is all I need for the method here. Okay, so I have to estimate these quantile functions. And I want to be able to go pretty far out into the tail because that's where a lot of the interest is in pretty extreme temperatures. So usually when you have you want to say something about like the 0.99 quantile, you would probably be forced to resort to using some extreme value theory. But here I've got 250 times, I've got up 12,500 years of model runs here. I think I can go pretty far out in the tail without having to rely on any asymptotic theory. I think I can use quantile regression and get way out in the tails with nothing terrible happening. On the other hand, it's certainly going to be the case that quantile regression will get more and more uncertain the farther out you go in the tails. No matter how you do it, there's less information about the far tails in the middle of the distribution. So what we did was say, okay, let's take the quantiles that aren't too far out in the tail, so between 0.1 and 0.9, we used that full model I showed you earlier with like 32 parameters in it. And then to do quantiles further out, instead of using all 32 parameters, we modeled exceedances beyond, say, the 0.9 quantile and used a regression with many fewer parameters. So this is different than directly using many fewer parameters for, say, the 0.999 quantile, because we're only using it for the exceedances. So to the extent that the fancier model affects the 0.9 quantile, it also affects the 0.999 quantile. So we think this is a kind of a good idea if you want to be able to go pretty far out in the tails, to use a simpler model for exceedances beyond the not so extreme quantiles. All right, I think I'm going to skip the bottom half of this page. I think it's too minor a point. And the top of this, yeah, so I'm going to skip this thing. All right, so there's some little finesses that I just skipped over there, and if someone's really interested, I could talk about them. All right, so that's a method, and I think it's a pretty good one, but how would we know? Right, I mean, we can wait 100, well, I can't wait 100 years. Probably nobody in this audience can wait 100 years. Maybe some of you could wait 40 or 50 years and see how well some of this works. So what do? Well, okay, we can play a game of using a second model as if it were the reality, okay? And I wrote a paper with some co-authors, some of whom you may know, probably a lot of you know Catherine Hayhoe, where we proposed this idea of replacing the observations by a second model and now playing the game of, from these three cells, trying to figure out what goes on in this fourth cell, and then using the fact that we actually do observe that fourth cell to test the method. And we were using this in the context of statistical downscaling approaches, and it seems to have caught on a little bit. It got I don't know how high profile this is, but this got a kind of, a separate little article about it, and they've since, I don't know who came up with the name, maybe Catherine, they called it the perfect model approach. But I think this is where it came from. All right, so okay, let's try that here. So we need a second ensemble, we need a second model, and it turns out, well, there is and this paper has just been submitted, and if people were interested, I could send you a copy. So we have a second model that we can work with. There's something called the lens ensemble that was done by NCAR, which happens to also be an initial condition ensemble with the RCP 8.5 scenario. It also happens to be CESM. It's at much higher resolution, and it has other things different in it as well. So this should be a very favorable, this should be an easy test for the approach, right? If I can't do well using the same basic model just at higher resolution and a few other things different, what makes me think this will work when I apply it to real data? So this should be an easy test. All right. So how do things work? All right, so what is this picture here? So this picture is just the differences between the two quantile maps. So those quantile maps are the transformation. You take a quantile in the present and you say how much is that quantile going to change in the future. And this is looking at the grid cell near Seattle. And so year 0 is 1920, and then it goes up to about 2090 or something like that. Okay, so they all start at 0 in year 0, because that's 1920. The transformation from 1920 to 1920 is the identity transformation, because that's the way the thing works. And so and if you look at the differences of 2 of those, they're all 0. So it's not saying the models are identical, it's just saying that the transformation you get from using this method of transforming from 1920 to a future year, those are all 0, because you're just transforming a year to itself. So it's kind of interesting. Actually, these things stay pretty near 0 for about the first 90 years. So that's saying that the 2 model runs agree quite well up to the present. And then they start diverging quite a bit. Is that a sign that these, that there's something funny going on? I don't know. You could argue, well, the climate's going to change a lot faster than the future. But you could also view this with a little bit of suspicion that somehow people have figured out how to make their models all look the same for the present, and then in the future they start to diverge. Okay, so the striking thing, though, is not just that they all start to get much warmer, but this is what I call bat wings. So what is that? That's saying that the higher resolution model thinks that Seattle winters are going to warm much more than the lower resolution model. Right. So the beginning and the end of the year, towards the end of the simulations, right, those are over 5 degrees. That's a big difference, right, in what the models think about how much the coldest temperatures are going to warm in Seattle. That's not, oh, we'll ignore that, right? 5 degrees is a lot by anybody's measure. All right, and here's something a little bit different. This is what's called a double quantile map. So you transform into the future using the lens map, and then you transform the future back into the past using the Shriver map. So if those 2 maps are the same, that should be another, it's just somewhat different than taking a difference. It might make a little more scientific sense. So we transform to the future using one map, we transform back to the present using the other map. Those 2 maps are the same. You should be back where you started, so if you take the difference between that and the original temperature, it should all be 0. So, okay, so this is now, we're showing a different representation. We're just showing the difference between 1990 and 2090, but we're showing the days, so as opposed to this one, where we showed you every year and then had a different picture for every quantile. Here we're showing you all the quantiles, and but I'm only showing you 2 different years. All right, but I'm showing you all the quantiles at once. All right, so you see in Seattle the same bat wing, right? Because again, so these are the highest quantiles, and the back is the lowest quantiles. This is again saying that in 2090, the lens ensemble thinks wintertime temperatures in Seattle are going to warm a lot more than the Shriver ensemble does. It's kind of interesting. It's saying in LA, Lens just thinks LA is going to uniformly warm about 2 degrees more than Shriver does, but with no obvious seasonal or quantile effect. So, I mean, you can do this wherever you want. These are just 8 cities that we decided 8 was about as many as we could fit into a plot without people's eyes exploding. And so, all right. So the models are pretty different. There's places where it's doing pretty well. I mean, Houston, I don't know, it's maybe not too bad. New York City is maybe not too bad, except in maybe the springtime there. All right. So we could actually look at the simulated futures and compare. So these aren't the direct test, right? The direct test is to actually apply the Shriver map to a lens run in the present and see how well it agrees directly with the lens run from the future. Okay, and because we have lots of lens runs, we can do that lots of times and get a very good idea of how well that works. So this is basically the method we're proposing, 1. Okay, we can compare that to the actual future simulations. So our hope is that 1 and 2 look the same. But another comparison we made is, what if we use lens to estimate its own transformation? So we use the lens transformation, apply that to a lens present run, and see how well that reproduces the future. If our method's working, that should work well, right? Because we use the same model, we made model 1 and 2 the same. Okay, and based on the pictures we showed before, we should expect that the Shriver ensemble, that the Shriver transformation is not going to warm Seattle's coldest winter temperatures enough. All right, so here I'm just taking December, January, February, so I'm glomming together all the winter months, which I don't like doing, but we decided this was the best way to illustrate this point. Okay, so let's see, which is which. So the initial temperature, these are daily average temperatures in Seattle. And you might think, well, first of all, it's only vaguely Seattle and it's model output. Where are all these cold temperatures? There are really not very many temperatures. This is actually the 0.01 quantile of the initial temperature distribution. So these are all rare events here. So it's not really saying Seattle gets all that cold all that often. All right, so blue is initial. What we're hoping to get is the black curve. Red is where you use lens on itself. So red and black should be very similar. So there's two things here. There's histograms, and then there's these QQ plots. So the histograms are, you're familiar with. They should look. The red and black histogram looks very similar. So in terms of the QQ plots, this black line would be perfection. The red is when you apply lens to itself. The red curve is very close to that black straight line. So they both say that, yes, the method works in the sense that if the transformations for the two models are the same, you will find that out and you will get an excellent future representation. So the green, though, is what we're actually doing. We're applying the Shriver transformation to lens. And you can see that it undercorrects, especially at the coldest temperatures, right? This gap between black and green is biggest at these very cold temperatures. It's noticeable but small at the warmer temperatures too. So, so does it work or not? Well, I would say, that's kind of problematic. And in reality, could easily be worse, right? So. Right, and here's the same thing for 8 cities. You see that for Los Angeles, again, that it just kind of undercorrects all across the distribution. So here we're just comparing the green and the red. I don't have the other distributions on here. Atlanta and New York, they look pretty good. So, I don't know, some places it works better than others. But in general, lens warms more than Shriver, especially at the coldest temperatures. And you can see that also. Houston is very good to the bulk of the distribution. But then if you get the far coldest temperatures, then it's definitely undercorrecting. All right, so, something that occurred to me thinking about this work is it's actually a fairly common situation where you use computer models, which you'll have models of different fidelity. So you'll have the really fancy model that takes a long time to run and the less fancy model that doesn't take so long to run. That's called multi-fidelity modeling, and there's a non-trivial statistical literature about that, although I don't think much of it is connected to the climate problem. But we could imagine, here both the lens and Shriver ensemble are big, the lens is a little bit smaller. You could easily imagine a situation where the low resolution model, you have lots of runs, and the high resolution model, you have maybe even only one run, right? And so what can we do with that? Shouldn't we be able to use that one high resolution? If we think the high resolution model is a more accurate representation of how climate will change, and we shouldn't necessarily assume that, right? Higher resolution doesn't necessarily mean better. But if it were, shouldn't we be able to use a single lens run to kind of adjust for that? And maybe I don't want to go into the details too much because I have a whole different topic I want to talk about. But the answer to that question is yes, in the sense that, so the red is what we want. The orange is using a single lens run to correct the Shriver calibration. And so except at the very coldest temperatures, the red and the orange points are basically indistinguishable from each other. So there does seem to be scope if you have a small number or even one run of a model that you think will give better estimates of changes in climate, you can combine that with an ensemble to get very good estimates of these transformations. All right. Okay, so I want to now talk about something completely different. If someone wanted to make a comment or ask something about this, yeah.
The one figure you showed before, not to come on back to it, but right where you have the Y scale is different.
Right, I didn't really explain this. So this is a density scale, so this is the scale for the histogram, and the right scale is a temperature scale for the QQ plot. So these numbers are the same as the x-axis numbers. So with a QQ plot, ideally the point should lie on the y equals x line. And so that's what the black is. Yes, you're right, I didn't explain that at all.
They're similar, you know.
Right, yeah. So these are literally density, and it's written once there, and this is literally the same as that, but I don't know how you could have possibly figured that out without you asking, so thank you. Yeah, this, we were just trying to think, how do you make a paper without a million figures in it? So we thought we could squeeze in both histograms and QQ plots into the same figure, and we're hoping people will be okay with that, but yeah. Oh, come on. All right, so in trying to think about what I wanted to do this year, so I was constrained by, well, you're spending next year in New Jersey, figure out what you want to do, as opposed to, I want to go here. So okay, said, oh, well, I know some interesting people at Rutgers, maybe I'll spend some time there. But I'd also thought it might be interesting to talk to some of the people at Climate Central in Princeton. And so one of the things they're interested in, and they work with Bob on this, is sea level rise. So I said, well, okay, maybe I'll try to look at some tidal gauge records. It seems like interesting data. And so off and on over the last couple of months, when I can find some time, I've been looking at some tide gauge data, and I'm going to tell you a little bit about that. But keep in mind that I hadn't thought about this problem until a couple of months ago, so I'm willing to be told that no, this doesn't make any sense. But I think hopefully I have some worthwhile points, even if some of the specifics of what I've done may have some problems. Okay, so there's a network of tide gauges all around the world that measures tides hourly, and my impression is that there's now a network of tide gauges that measure water levels every minute. I don't know if they're stored every minute. You go to the NOAA site, it seems to show every 6 minutes, but maybe they actually store them every minute for some sites, and that would be interesting. I really like high frequency data. I think it's really interesting to look at. Okay, but I'm looking at hourly data. Okay, so obviously one of the main interests with water levels is the extreme highs, because those are where most of the damages come from. All right, and so you could just say, well, why don't we look at just the water levels themselves and analyze those, because those are a direct measure of what we're interested in. But it's apparent that throws out a lot of the information, because a lot of the variation in water levels is due to known periodic tidal components that we know about, and to not use that information in the analysis just seems wrong. The problem is how to actually use that information. So in particular, it might be tempting to say, well, at any one site, so there are these predicted tides. So NOAA has its predicted tides, and we'll talk about that a little bit. Why can't we just add the highest predicted tide to the highest residual water level above the predicted tides and say that's might be a good way of saying what the worst can happen. Let's combine the worst predicted tide with the worst observed residual. And the problem is that may not be realistic. That how much you can get above the predicted tide may depend on where you are in the tidal cycle, and so that may give unrealistically high estimates for what can happen. Okay, so some time ago there's been a claim, and there's a bunch of papers that try to support this, that something called skew surge, which I will define in the next slide, is independent of the predicted tides. And so if you had the predicted tides and skew surge, and they were independent of each other, then that would make this problem of trying to make inferences about what are realistic extreme high water levels, that would make that, while still using the predicted information, that would make that problem much easier to do. So it would be great if it were true. All right, so let's look at this a little bit. So, okay, so I'm assuming not, some of you know what skew surge is, but maybe not all of you. So here, so most of it, all the analysis I'm going to use is going to be at a site in Mayport, Florida. The only reason I picked that is because talking to the people at Climate Central, you know, well, Florida would be interesting to look at. And this is the longest running site in Florida. Unfortunately, it's shut down in about year 2000. There's another tide gauge in Mayport now, but it's, I guess, in a slightly different location because it has a different number. Okay, so for each tidal cycle, you get a predicted max, and then you get an observed actual. And so here, in this one, they occur at the same hour, and the skew surge is this difference. At the next tidal cycle, they don't occur at the same hour, but the skew surge is still the difference between the two green circles. Okay, so for each cycle, you look at the observed and the predicted max, and you look at that difference. Okay. All right, so where do those predicted cycles come from? Well, they come from NOAA. What does NOAA do? I still don't actually know yet, although I haven't exhausted all the opportunities. Bob knows someone at NOAA who claims to understand what exactly they're doing. So what you can find at the NOAA site is there's 37 different frequencies for which they assume that there's a sine and a cosine, and somehow they estimate the parameters. And those 37 frequencies include lots of things that you could think of. But it's also the case that not every frequency is used at every site. But every site uses some subset of these 37 frequencies, so there's potentially 75 parameters that somehow have to be fitted at each site. And I don't actually know how that's done. Except that when I looked at their data, I found out that can't possibly be right. There are clearly other frequencies that they're using. In particular, what I'm pretty sure I discovered, someone that knows this, is that there's an 18.6-year tidal cycle having to do with the plane of the moon's orbit is not the same as the plane of the Earth's orbit. And I don't think they're including that, but they're including interactions of that cycle with other cycles in there. And I still don't know then how they estimate the parameters that they fit. And I don't know how they decide which frequencies to use. But in any case, you know, no matter how they did it, whenever somebody assumes something is independent, that makes me worried. So one of the things I teach in every statistics course I teach is that the biggest mistake that people make in analyzing data is assuming things are independent when they're not. And by biggest, I mean that it's made all the time when it's unwarranted, and the consequences of making it can be severe. Okay. So I would rather, can't we do something? Can't we use information about the predicted tides to get better estimates of extreme water levels without assuming independence? Okay, okay, well, I just, you know, told you about using quantile regression. Maybe we can use quantile regression here as well. So what am I going to do? I'm going to do quantile regression, and I'm going to try to predict the observed tidal maxes, and I'm going to use as predictors in my model the NOAA predicted tidal max, but I'm also going to use, I just guessed this one, it seems to help quite a bit, the previous tidal minimum. That seems to contain information about the observed max. I'm going to try to refit some of these frequencies. So I decided to pick the first four. I could try to tell you more about why. I specifically wanted, annual cycles are definitely in the NOAA frequencies, but you know, I didn't believe they had them right, so I put in some annual frequencies and harmonics. And I also put in a linear trend in time, which is not contained in the NOAA predicted tides. I think that, so maybe someone will tell me this is wrong, but I don't see why we shouldn't just scrap this approach. We know for the last 80 years where the moon, the Earth, and the sun have been. Why can't we use that information directly to build a predicted tidal model? It would have fewer parameters, and I think would actually be more flexible. And at least at sites where you had long records, my guess is this would produce noticeably better predicted tides. But maybe that's just not right. All right, so I'm going to use quantile regression, and I'm going to first estimate the median of the distribution by using this method. So I'm just trying to correct the skew surge. So if skew surge, I'm just trying to refine the NOAA predictions. If the NOAA predictions were already as good as you can possibly do, none of my coefficients would show up being significant. All right, but that's certainly not going to be the case. I also want to look at the scale of the distribution. For my estimate of the scale of the distribution, and look at the difference between the 0.9 and the 0.5 quantiles. And I'm not going to, and I do it just on the upper side because I'm more interested in getting the upper tail of the distribution right. So I don't really care if I've mismodeled the lower tail of the distribution. All right. And I use fewer covariates when I estimate the scale than when I estimate the location. All right, so like I said, I looked at Bayport. This has 73 years of data. Very little missing. I mean, there is some missing, but very little. And for the median regression, I explained 19% more of the variation in the observed tidal maxes than NOAA skew surge. That's actually a pretty substantial amount. I mean, if you were thinking in terms of an R squared, you should kind of double this number, right? Because this is more like an R rather than an R squared. The slope is very noticeable. It turns into 1.8 centimeters per decade, which is a non-trivial amount, if that can be believed. And so so the S's are for about the first year of the model development. The S's are the NOAA's predicted tidal maxes, and the C's are my corrections to those. And you can see both of them have these crazy patterns because, of course, tides have this weird alternation to them, whether the moon and the sun are working together or working against each other. It's kind of hard to follow the pattern. But the corrections, they're not as big. I mean, so the NOAA predicted tides do actually tell you quite a bit, but the corrections are not that small compared to the NOAA predicted tide. So the corrections are pretty substantial. If we look at the scale estimate, some things still seem to be clearly significant. There seems to be maybe a hint that there's a slope so a positive slope here would mean that the spread in the skew surges was getting bigger over time. But this 0.2 is much smaller than the one, it's an order of magnitude smaller than the last one. Okay, so now to get beyond the 0.9 quantile now, because I don't have so much data, I am going to use an extreme value approach. I'm going to get what's called a generalized Pareto distribution. There's theory that suggests that that shows that upper tails of many distributions look like this. It has this weird form here. I don't really want to go into the details. In principle, I could let the parameters of this distribution depend on seasonal cycles and other things. I couldn't find any evidence that helps, so I left it out. And in some sense, the interesting parameter here is this C parameter, which is called the shape parameter. It controls how fat the distribution is. In particular, if C is positive, the distribution's a very fat tail. If it's negative, it's a very thin tail. I guess people would tend to think that coastal water levels would tend to have a positive parameter because if you have hurricanes, you have these kind of weird outlying big events. The estimate is only slightly positive, and it's not even close to statistically significant, even under a bogus uncertainty analysis. Okay, so the uncertainties I'm talking about here assumes that these residuals are independent, but of course they're dependent in time. Here's just a time series plot of the first year of them, the last full year of them. And there's clearly strong, on short time scales, time dependence. So standard errors that assume they are independent are really a bad idea. We could try modeling all of this and coming up with an answer, but I'm going to do some form of resampling again. So before, when I had an ensemble, the resampling was easy because I could just resample ensemble members. Here I only have one reality, so I'm going to resample years. I'm acting as if years are kind of independent. What happens in one year is independent of what happens in another year. I think for this quantity, that's probably not too bad an assumption, but it's not perfect. But I'm going to use that. It's much better than ignoring the dependence. All right. So what happens here? So I don't want to go into too many details, but so one of the things I had added in my regressions is I said, well, I've got 70-something years of data. Why don't I just put in the 18.6-year cycle? That looks statistically significant when I ignored the dependence. Now in this block bootstrapping, it no longer looks statistically significant. Now there's no evidence that the linear trend in time in the shape parameter is significant. All right, so let's see. Okay, so now we can ask, well, have I squeezed out everything I can in terms of my predictions? And And I want to look at are there missing periodicities? Well, so spectra are a good tool for looking for periodicities, but there's so much short range dependence that might make it hard. So I fit a standard time series model. I'm almost done. And then I looked at the residuals from those, and I looked at the spectra of the residuals from that. So, okay. And what you see here is this bunch of frequencies near the highest frequencies that have these strong peaks to them. Okay. So those are clearly a sign of missing periodicities. I'm pretty sure that they are interactions between the every other. I think I know where they're coming from and that they could be corrected for. Okay. What do I want to say? Okay, so there's 3 more slides. We can try to use these to say something about the predicted high tides. Is it reasonable to add the biggest high tide with the biggest skew surge? Well, if you use either the NOAA predictions or the predictions that I've shown you, that's not true. It's pretty clearly the case that both the NOAA prediction and the prediction I show you over-predict the highest predicted tides. If you make a correction for that, you actually get something that's pretty reasonable. I actually think that if trying to combine the biggest skew surge with the biggest predicted high tide gives a somewhat unrealistic high water level for this site, but maybe not wildly. Okay, so let me just make some general comments. All right, there's clearly more I need to do here. I've only looked carefully at one site. I've looked a little bit at Montauk, and some of the same problems don't happen there. If I'm really going to, do this on an industrial scale, I'm never going to do it myself. So if you think that this sounds interesting and you have a student or postdoc who might be interested in working on it, I'd be happy to talk to you about that. I think some of the specific methods I've shown you can be improved. And the reason I got interested in this data, I haven't shown you at all. What's really interesting about the tide gauge data, there's a small number of tide gauges that run for 50 or 70 years, and there's a huge number of tide gauges that ran for a year and then got moved or shut down. And how do we combine those to get a complete kind of spatial map of how water levels are changing? Maybe I'll skip this one. I should say that one of the groups in our class is working on an extension of, and most of the people from that group are here, looking at not just temperature quantile regressions, but temperature and humidity simultaneously. That's clearly of interest for heat waves because it's not just temperature that causes the problems, right? It's temperature and humidity that are both high at the same time that cause problems. I have what I think is an interesting way of doing downscaling of precipitation. If anybody thinks they want to talk to me about that, as a student or postdoc with good computing skills. All right, and now just some very general comments. This should be completely transparent to all scientists, but to statisticians, some of them don't seem to get it. But if you want to do statistics, you need to take data seriously. I've tried to do that here. You might disagree, but I think I've tried. You have to worry about what was measured and how it was measured, and you have to think about how the science relates to whatever statistical method you're going to use. I want to point out that resampling methods, block resampling methods are a very powerful tool for getting uncertainties about complex quantities when you don't know how or don't want to model complex space-time dependencies. I think they should be used much more than they are, and I'd be happy to talk to people about that. Another interesting thing that I found is ensembles are a really cool tool just for statisticians, because you give us these multiple versions of reality that we can now test our statistical methods on. And so I think there's a lot more that can be done there. And just a general comment about cross-disciplinary collaboration is it's immensely difficult. It takes a lot of patience and persistence. I'm not sure how much I have of either, but I definitely have more of both of those. I have more patience than I had 20 years ago. Maybe I have less persistence, so I don't know how that balances out. But thank you for listening to my talk today.